So just to quickly introduce the setup we got here, there are a few different cameras. There's obviously one for my face, there's one for any handwritten notes that we do, and then there's going to be the screen share where I'll mostly be directing my attention with all the pre-written stuff as well as a textbook. So feel free to pin any of those if you want to do it that way. I feel like you can pin multiple as well if you right click one of the windows. So it might be good to have probably both the handwritten bit and the screen share up, or maybe just the screen share up. But okay, so the agenda for today is to go through some of the linear stuff. So we're talking linear geometry stuff in the sense of gradients and midpoints, and extending that out into simultaneous equations side of things. So if you have any questions as I'm going through the lesson, feel free to just shout out, put something in chat, however you want to interact. More than happy to go back and revise again. Cool, okay. Can you see all those screens easy enough? Shout out if you have any issues. Okay, so distance. So if you have any 2 points on a graph that are known, you can always find the distance between those 2 points using the distance formula. This is effectively just the rearranged version of the Pythagoras formula, your whole a squared plus b squared equals c squared thing, where you're effectively finding the hypotenuse of a mock right-angled triangle. You essentially have some horizontal component and you have some vertical component. You're simply finding the difference between the two heights. So this one had a height of 6 and a height of 7. Distance between those two, vertically speaking, is going to be 1. The horizontal distance, well, you have a -2 and a 4. That's a total span of 6. So you have your difference in x values, your difference in y values, and the rest of that is just Pythagoras, the rearranging to get the c on its own, as you can see here. So if we want to do that with an example, find the distance between these 2 points. If you just use the distance equation, you don't have to memorize, it's Pythag. There's no real need to, it's just kind of nice to know where it comes from, just in case you forget how to actually create this equation. So as long as you know the equation, go ahead and just label the points, which is probably the best way to do it. Don't just leave them as point and point. It's probably best that you put a little x1, y2, x1, y1, and x2, y2 on them, so that when you're actually subbing that into the equation, you don't put into the wrong spot. This one's a bit more forgiving than most other equations, simply because when you do your subtraction, you're squaring it afterwards. So even if for whatever reason you did do these back to front, the square still pulls a lot of weight in helping you not make that mistake actually matter in the end. I don't know if you'll still get marked poorly for your working out. I doubt it. But it is worth pointing out that there is a bit of forgiveness in this equation, more so than others. And yeah, I mean, the rest here is just simplification. This is just very basic algebra type stuff. Any questions so far on how that works? Next up, midpoint. Midpoint, we kind of know from when we work with data how to average a data set, which would simply be you'd add all the numbers up and then divide by the number of numbers that you had. That's the very basic way of finding the average of a set of data. Midpoint's very similar. We have 2 points and we're essentially finding the average of each of those x and y components. So you essentially add up your 2 x values and halve it, halving it because you have 2 points. 2 points of data. Same with the y values there. So in theory, if for whatever reason you have 3 points, these would just be a division of 3, and you'd be adding up again all of the x and y components, always dividing by the number of points that you have. Doesn't come up pretty much ever. I don't think it ever has, but just in case, you can extend that out to multiple points. Again, this is just substitution. There's nothing too crazy to talk about here. Again, probably just labeling what each of those are rather than just leaving it as P1, P2, just to avoid the mistake of putting things in the wrong spot. You can see I literally go out of my way to label them as what they are before subbing them in. But that's just potentially overly cautious. And that's what that would look like if you're finding the midpoint of the line joining 2 separate points. Gradient. So gradient, as we should all be familiar with, is going to be calculated by the rise over run. How high did it rise and how long did it run for? It is the slope of the line. So if you're looking at an actual line, it'll be the slope of it. If you have two separate points, then what you're finding is the slope of the line that would have connected those 2 points. So for instance, you might have a point over here and over here. You're looking at the slope that would have connected those 2 points. Gradient is always observed left to right. So if you are rising from left to right, you consider that as a positive gradient. If you are falling from left to right, we consider that a negative gradient. That's more so observation. If you're literally just doing the equation, that will always come out to be positive if it's going up and negative if it's going down. But it's nice to have these little shortcuts to know, hang on a minute, if I get a positive number, does that actually make sense if I were to dot that out on a graph? If you dot it out on the graph and you got a mismatch, for instance, if it was falling, but you actually calculated a positive gradient, that's a sign to you to say, hang on a minute, should probably try to recalculate that. But again, just substitution there. Any questions so far? This is all just revision of linear. Okay, parallel lines. So two lines are considered parallel as long as they share the same gradient. So questions in the textbook and even in the exam will go out of their way to say parallel as opposed to they have x gradient, whatever that gradient would be. We see this a lot actually later on in differentiation in the calculus chapter, which is a study about how gradients work for non-linear things. So linear being straight line, you know, your quadratics, your polynomials. How do we do gradients for those things that are curves? And what you'll find is one of the key things they'll mention is in particular questions will be that the line is parallel, and that is your indicator to know, hang on a minute, okay, that just means it shares the same gradient. This is a lot more basic than that though. We're just trying to find parallel lines to other linear lines. So if we just remember our basic y equals mx plus c, we can know right off the bat that if we're parallel to this line, then the gradient must therefore be 3. They have to share a gradient. So immediately off the bat, we can say, yep, the m of our next linear is going to be 3. Now, the other complication is that it has to pass through a specific point. So again, if we have our y equals mx plus c and we chuck in that m equals 3, we have a few unknowns in that equation. We got y, x, and c. Now, when we're creating an equation, y and x, perfectly fine to have in there. You want those in there. But we do want to figure out what c is going to have to be. Very often the case is that you would sub in some point or other information that you have to make sure that c is the only unknown. This is just generic stuff that you can apply to literally any equation, linear or otherwise. In this case, we know a point that it has to go through. Sub in the x equals 1, the y equals 5, and, well, c is the only thing left in there. So chuck that into your linear, and sure enough, we get that parallel line. So if we were to plot those one against the other, we have our original graph, and we have the red parallel graph that goes through the point that we were trying to make it go through. Anything to clarify there? Cool. Perpendicular lines. There's a few ways to represent this. For whatever reason, the textbook likes to do it this way, where they say the product of the gradients must equal -1. I've always preferred to say the gradient of the perpendicular line must be -1 divided by the gradient of the line that you're trying to be perpendicular to. Perpendicular just means that it meets at a 90-degree angle. So if we have a look at an example here, there would be a right angle on the intersect between these two lines. That's what we're trying to achieve with a perpendicular line. This has applications in physics, actually. So one of the things you want to do in physics when working with like forces is to try and figure out what is normal to the thing that is in motion. You'll see that with like cars going around a raceway that have banked curves to them, so they have like a slight angle to it. We're essentially trying to figure out where the forces are going, and this is one of the applications of that. So how do we do it? Well, again, it's just going to be these equations, but very similar. So we're trying to find perpendicular to that old line that we had through this other point. That tells us that, yes, the gradient was 3 of the original. So to get the gradient of the new one, we're going to do -1 divided by 3. So it's always -1 divided by whatever the gradient of the original line is. And then the rest of this just follows exactly as it was before. Sub in the point, simplify for C. You'll find that when you do normal lines, you get a lot of these fractions. That's very common. Yeah, very common to have those fractions, and very common to have negatives in there as well, simply because you're doing -1 divided by a number. And again, that's what that looks like. And that's the summary. So that's all of the linear geometry side of things, or at least the introduction to a linear geometry side of things. Anything to revise there before having a look at simultaneous? Okay, simultaneous. There's a whole bunch of ways you can do simultaneous. We'll look at a few of them. The very bare bones basics of doing simultaneous equations would be to do a substitution approach. You'll technically always be doing some form of substitution in simultaneous, and also some form of substitution in pretty much any time you're working with an equation. When we're talking about simultaneous equations, we're specifically talking about linear simultaneous equations here. So you have two separate linear equations, and sometimes you're trying to, like in this case, you're just trying to solve what are the two options, what's x, what's y in this scenario. As we'll see later on, there are other ways you could do simultaneous equations depending on how many unknowns are in these equations. Anyway, so what's substitution? Well, basically, we have an x and a y in both of these equations. One of the things we can do is rearrange at least one of them to have one variable on its own. Doesn't matter which one you pick. In this case, I've taken equation 2 and rearranged it to have x on its own. Because these equations have a match, the x and y from one of them is the same as the x and the y from the other. So if I have this statement that says x is equal to 7 plus y, all I've got to do is replace the equation that I did not rearrange with that new version of x. So instead of putting an x in this spot, I've copied it down over here as well. Instead of putting an x in that spot, I now put the 7 plus y in that spot. Suddenly, I only have an equation with one unknown, which is prime and ideal for us to try and solve. Expand, simplify, 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 simplify. We get our one unique solution, y equals -3. Once you have that, it doesn't matter which of these you substitute into, which of these you put a -3 for the y on, you'll get the same answer for x either way. So, because it doesn't matter, pick the easiest one. This has a few multiplications in it. This is just a single subtraction. So I would go out of my way to put it in the easier one rather than the harder one. And that's a set of solutions to the simultaneous equations via substitution. Any questions there? Next up, elimination. So this is a bit of a weirder approach to algebra, where kind of like how we can add and subtract both sides of an equation to do basic algebra, right, like rearranging an equation, we can also do that arithmetic on entire sets of equations. So for instance, what we could do is we could take equation 1 and add it to equation 2, or subtract it from equation 2. We can do full arithmetic like that. But before we do that, what we're effectively trying to do is rewrite one or both equations such that at least one of the variables shares a common coefficient. So in this case, this one has a 3 on it, this one has a 1. This has a 2, this has a -1. None of them actually share a coefficient yet. So pick the easiest one that you can get to. In this case, I've chosen to get it to the 2 on this y. So what I'm going to do is take this equation 2 and multiply both sides of that equation by 2. That's going to get a match. 2 over here, 2 over here. Yes, one's negative and one's positive. You're just looking for a number match rather than a sign match. And the reason why is because when you actually do the arithmetic afterwards, you can compensate for that. But if you really wanted to, you could go ahead and be like, yep, I'm going to do a multiply by -1 on both sides, and then that'll get a perfect match. You don't really need to do that though. So what do we do from here? Well, we want to figure out what arithmetic should I put between these two equations such that it would cancel out one of those terms. So in this case, I have a 3x and a 2x. Add or subtract, nothing's going to cancel. We have a 2y and a -2y. Only adding those two things would cause them to completely disappear, which is why what we're going to do is do equation 1 plus equation 2, which works as you may expect, which is you do the x terms added together, so 3x plus 2x gives you the 5x. The y terms added together, which, well, there's nothing there anymore, it's cancelled, that was the whole point. And then the constants will add together, 6 and 14. That is another way of eliminating a variable. From there, just rearrange. X is 4. And you can see even the elimination method also uses substitution in the very end, which is saying, yes, we have x equals 4, shove that into a spot where we, into one of the equations to get the other unknown. So you're always using substitution. Elimination can be helpful in mainly circumstances where you can knock out two variables at once. Now that's not going to really happen for linear, more so for like, well, maybe I guess it's technically still linear because there's no powers in it. But when you have a lot of different terms with like x, y, z, all of those, sometimes you can knock out more than one variable depending on how you do your arithmetic on this. That's where it starts to shine a little bit more. But for linear, you just honestly just pick whatever seems easiest for you to do. Unless your SAC, for whatever reason, is going to tell you to use one or the other. I can tell you for certainly the exam will not force you to do one way or the other. That's the fundamentals of simultaneous. Before I get into any more complications there, anything to clarify on any of those approaches? Easy. So, what we get up to next is this idea of literal simultaneous equations. It's a weird name for it. It just means that there's one more coefficient in there. So instead of having both x and y, now you have an additional, usually they use k in there as the other coefficient, maybe a sometimes. Now, when you have more than three variables and only two or three or more variables, only two equations, suddenly you can't get a unique pair of solutions always. And so basic theory of equations is that if you have x number of unknowns, you need to usually have x number of equations to solve those unknowns. For instance, if you have 3 unknowns, you would ideally need 3 equations to get a unique solution for each of those. We only have 2, but we have 3 unknowns. So we have to settle for finding solutions in a slightly different approach. There's a few different things that could be asked. So sometimes you'll be asked to figure out where do these things have no solutions, where do these things have one solution, and where do they have infinite solutions. So we'll go through what that actually means. It's easiest to think about it graphically. So for instance, a unique solution just means that the two linear equations that you have meet at a single point. That's it. That's all it's got to do. It's got to have some unique x and y pair that it matches. For infinite solutions, it just means that the lines become exactly the same. They are completely overlapped from each other. They have the same gradient, the same y-intercept. They are the same equation. That's what it means to solve for infinite solutions. You pick your value of k to make them absolutely identical. For no solutions, that's just another word for parallel. Reason why is because they don't touch, ever. There is no crossover between the two lines. And so all we're going to do is figure out, well, okay, what is it that makes linear lines parallel? Same gradient, different y-intercept. Those are the criteria you're looking for when you're trying to find or solve for k such that there is no solutions. Which I feel like there's a typo here now. Let me write a note to fix that. Maybe it's a typo, we'll see. Typo. Cool. All right. So, unique solution. How do we actually go about doing that? So, to have one crossover point, the only criteria is for the gradients to be different. As long as the gradients are even slightly different, they will eventually cross over at a single point. They have slightly different slopes. They will never always run in parallel. They'll just hit each other at a certain point. So how do we make the gradients different? Well, usually you get them in this scenario here. My preference has always been to rearrange to get y equals mx plus c. That way I can very clearly see what's my gradient, what's my y-intercept, and then go from there. You don't have to do this. There is another way involving matrices theory, but matrices haven't been in the study design for a couple of years now, so we'll leave that there, unless someone's really keen on doing it. So rearrange, bunch of weird letters in there, but you know, this is still just going to be algebra fundamentally, and you'll get something that looks like this. You get equation 1, equation 2. Now, in this case, because we're looking for gradients to be different, I've just said, here's the gradient of the first one, k over 3. Here's the gradient of the second one, negative 4 over k plus 7. And I mean, I'll put a do not equal sign there. It's fine to do that. In fact, it's technically more accurate to put do not equals rather than an equals sign, because you don't want them to be the same. But technically speaking, you can just go through it with an equal sign and then just say at the end, ... therefore k should not be negative 3 or negative 4. As for how you get there, you still treat this do not equal sign the same as a regular equal sign. You can still multiply both sides by the denominators. You can still expand out to a quadratic, factorize, or otherwise to solve the solutions for that quadratic. So what this is telling us is, as long as we don't pick k equals negative 3 or k equals negative 4, whatever happens to these lines, they will always cross over at a single point somewhere. So you never actually find out what the x and y is for that crossover, but what you do is you find under what parameters they would cross over somewhere. Is it clear enough what's achieved there? Let me know if not. Infinite solutions. So we're going to use the exact same approach here to try to make them identical. So I'm just going to, well, actually, apparently I just borrowed everything from before. So we found earlier that the gradients would be the same if we had k equals negative 3 and k equals negative 4. So just to save some space, I didn't rewrite all that, but you could go through and go, yep, okay, get my y equals mx plus c, do this exact same thing again. You're going to get that k equals negative 3 and that k equals negative 4 for identical gradients, which is a good thing because we want them to be the same. The lines should be the same. But only one of those k values is going to also have the same y-intercept as well. So let's just test one. Literally just pick one of them, and what you're going to do is have a look at the y-intercept component of both of those and just shove whatever test value of k in there into it and see, do they come out to be the same thing? So this is me making the, actually I'm doing it slightly differently here. I'm making the y-intercepts equal each other and then solving based on that. Probably better off, instead of going through and doing that, just taking one of these k values and then testing. You can see that if you go out of your way to solve the whole thing, probably going to take a bit more effort, and you're going to get the same solution anyway. You can see the match there is k equals negative 4. And if you're still not convinced based on your working out there that you haven't got the right pairs, solve them in, see what happens. Just chuck it into the original equations and then see, do they become the same thing? Sure enough, they do. And then no solutions. Again, so we're just going to borrow from before. Cool. Gradients are going to be the same if k is negative 3 and if k is negative 4. We do need the same gradient for parallel lines for no solutions. But we need different y-intercepts. So the conclusion is just going to be, if you did it this way, you'd say, okay, well, negative 4 made it the same. Negative 6 is going to make it different. Or otherwise, if you did the substitution method where you just plug in and test one of these, you would just say, cool, I tested this one, that gave me the same, the other one must therefore give me different. And once again, if you want to test that, feel free to just shove that into the original equation. Whatever that test was, you would see, cool, these both have a gradient of -1. That's perfect. That makes them parallel. This one has a y-intercept of 0. This one has a y-intercept of 1/4. Different, therefore parallel. Cool. Anything to clarify for those? Okay, so this is something that came up. When did it come up? It's pretty rare, actually. It came up early into the new study design, and then I haven't seen one of these for a very long time anymore. This is how to find a general solution to this sort of thing. So they haven't asked you to get a particular thing, no solution's infinite or unique solution. They're just saying, what's the general solution between all of these things? I'm going to have a look at a couple ways to do it. We'll do a tech-free approach and then a tech-active approach. That being said, I've only ever actually seen them as tech-active, but just in case, we'll do a tech-free as well. So if you get a multi in a tech-free, essentially all we're going to be doing is picking what your parameter is going to be. So it's kind of like how we had k that was considered the parameter. For whatever reason, they like to use the Greek letter lambda for this. So we're just going to pick one of x, y, or z to be lambda. If you're doing a tech-free, again, you can pick any of these. If you have a multi in front of you, you probably want to pick one that's at least on the multi-sheet. Otherwise, you're kind of just wasting your time. From there, rearrange all the other variables in terms of lambda. So for instance, if you chose to let y equal lambda, then your first equation, instead of being y plus z equals 2, you rearrange, so that came from here, by the way. Instead of having that, you rearrange to get z on its own and then replacing the y with the lambda. Same over here. This one also has a y. So, in fact, yeah, what you pick is probably going to be decided by what is shared between the two of them. So this one has a y, this one has a y. There's nothing else that's actually shared between them. That'll be the best variable to pick. Not the only. There is a lengthier way to do it with non-shared variables, but yeah. Anyway, just rearranging both of those, we now have x, y, and z purely in terms of lambda. So then you just look at your list, or if you're doing it with no multi, that's just is your answer. You're there's no real way to error check this one anymore, or at least no easy way to error check it. But yeah, if you have a multi-list, just look at it and then be like, cool, that's the one, that's the match. Awesome. Tech active, what do we do here? I've got to actually remind myself on this one. So we reuse the simultaneous equations solver in the CAS. This is the TI Inspire version. I only actually, yeah, it should work on both. There's no reason why it wouldn't. Anyone have any trouble getting to the simultaneous equation solver on their CAS? Everyone know where this is? Happy to show if not. But otherwise, what you're essentially doing is taking the two equations that came from the question and then toggling this third equation in there. That is you choosing whatever letter equals lambda. Now, I can't find lambda on my CAS. I'm not going to go out of my way to do that. I'm just going to put another letter in there, k. So, do you need your CAS? No, this is fine. I mean, ideally you'd bring your CAS with you in case we do anything CAS related. There's going to be recording as well to look up things. There's no worries at all. So if there's anything you need help with on the CAS, ideally have it. Otherwise I can just do it on the recording anyway. But okay, so the reason why we had to put this third thing in here is because the CAS doesn't really like doing simultaneous equations unless there's the same number of unknowns as there are equations. And so what we're doing is, sorry, say that again. The unknowns that are in here has to be a match to the number of equations. We do in fact have 4. There is going to be a k there, but you need a match here. When you set up this structure in the CAS, there will be 3 slots for it. You can't leave. I don't think you can leave one of them empty. Either way, we're going to make use of it. What you're going to do is look at this list of variables that have the lambda in them as only lambda, and then just go through the full list, and that final equation that you have is going to be exactly that. So z equals, well, I'm going to say k. You get your list, and then you compare. Did we actually get a match on the list? In this case, we did not. I won't go through and say why each of these is not a match. It's literally just look and then see. Then you just choose the next one. So you can see these are identical with the exception of the fact that we're now choosing x equals k. So you can see now x gets k, and then everything else is rearranged in terms of the x equals k. Those aren't a match either, so finally we're going to choose one we know is the case, y equals lambda, and that is also going to give us the match now. Just keep in mind that Kaz likes to do factorizing for whatever reason. It'll bring negatives out where possible, whereas in this case, in our list of options, there wasn't really that, especially for the two-digit options. So just keep in mind you won't get like a perfect visual match. You might have to do some rearranging. But yeah, I haven't seen something like that for a while, but just in case it comes up again, that's in there for you. That's what a general solution to these are. You're not solving for any of the variables really, k, x, y, or z. You're just kind of getting them in terms of each other, which is the best you can do under those circumstances. Anything to clarify in not just that, but any of this so far? If not, we'll move into some practice. Easy. Okay. So I've got a Word doc that I'll chuck in the chat. That is basically where you can practice the things that we just covered. So this is going to be from chapter 2A to 2E of the Unit 1 and 2 book. And what I've done is I've bundled all the questions from those chapters into certain groups based on how similar they are. Like for instance, if you have a look at 2A here, this is, the first question is, you have 2 points, find the midpoint. The second question is also, you have a couple of points, find the midpoint between them. So I would consider those to be basically the same question. Yes, there's 3 points here, but they're saying do the midpoints of each pair. So it's still the same thing. Yeah, cool. So we'll smash through a few of these. If this is too trivial, like if we're getting them fairly easily, we'll just move on faster to the next unique thing. And if not, we'll go through them in order. Cool. Let's start with a real basic one. 1A. Just find the midpoint between those 2 points. If you need a copy of the book of your own, let me know. You should all have one though.
Is it 5/8?
Yep, 5, 8. Absolutely. So that would have been from this. Just adding the 2 x values, dividing by 2, adding the 2 y values, dividing by 2. That's the same as all of these. Does anyone want to go through any more of those kinds of questions? Maybe even this one actually, because this one's got a bit of a picture to it. Let's see what we got here. Organizing 2 meetings. One is a hill climb from this point, and the other is a circuit from this point. And we're trying to figure out where an ambulance should be put such that it's halfway between the 2 points that were mentioned. Not actually different, but there's a story behind it, so this will test at least a little bit of comprehension, perhaps.
Is it 6 and 8.8?
6 and 8.8 is perfect. Yeah, exactly the same as before. Midpoint. Nice. A little bit different here. So now we're chucking in a few letters in there. We don't just have point and point, although we do. It's just that the other point that we have is with letters as opposed to numbers there. So in this case, we want to figure out the midpoint joining these things in terms of A and B. And then, if this was the midpoint, what would A and B have to have been? Bit different, slight extension on that. 9 comma negative 6. Yeah, so that would have been A equals 9, B equals negative 6, yes. That is what you, yeah, that is what you would have meant there. Because I don't think the point itself wouldn't have been that, because the points were, they had other things attached to them. So it would specifically be A equals 9 and B equals negative 6, but otherwise, yeah. Yeah, that's that. Oh yeah, here we go, distance. This is just a fundamental of distance formula. See if we can find the distance for 6A between those 2 points.
Five root two.
5 root 2, yes, that's it. Actually, I think I was wrong about this. I was looking at the solutions in the back and it made it look like there was more into it. It does in fact seem to be the case that that point you wrote was actually fine. I'm just looking at the wrong, or something different in the background. Oh, this actually had it at 2 decimal places. That's weird. But yeah, that's whatever. It's 5 root 2. There's an interesting take on it. They're not actually spelling it out too much for you there. They're saying calculate the perimeter of a triangle with those vertices. So it's slightly buried what they're asking you to actually do, or how you would go about it. A bit more reading comprehension. And yeah, so Kaz would definitely help out a lot with doing these. Point of order, if you're not too familiar with this book, the book is pretty ambiguous on whether it's deciding to use Kaz or not for certain questions. Sometimes it has the Kaz icon there, sometimes it doesn't. Like if we have a look at this, it said 2 decimal places, but it just didn't put the Kaz icon there, which, I mean, I don't know about you, but there's next to no way you're going to be doing a root by hand and converting that to a decimal place. Probably not going to happen. This one might be the hardest one, both by length and a little bit by the wording of it.
Chris, is the answer to question 7 like 30.73?
30.73 is slightly bigger than what they had in the answer. Should be 29.27. Although I imagine it was just...
Must have just been something wrong with mental maths.
Yeah, probably just a minor typo there with the mental math. Because the three roots that you would end up with would be as follows. Like that. If we have a look at the handwritten doc. Root 97, root 85, root 104. That's what this come out to be. Let me just double check actually. Yeah, okay. They didn't have a typo.
Yeah, I just had the last root wrong.
Yeah.
My bad.
Okay. Yeah, so that was just going to be a sequence of distance formulas between each of the vertices. So you'd do a distance formula between the -3 and the 1, the -3 and the 7, and then the 7 and the 1, those points, adding them all up. So very lengthy, but yes, perimeter is in fact a distance, so we should use a distance formula for it. 8's going to be a bit of a time waster, so basically they're saying, here's a bunch of points on a Cartesian plane, here's two midpoints, so midpoint 1 is called P, midpoint 2 is called M, what's the distance between those midpoints? So what you would essentially do is find the midpoints that were described using the midpoint formula, and then do a distance formula on top of all that. Just because we're getting close to ending, I feel like we should probably leave that one. Unless you want to give that a practice, but stuff you've done already. We have a thing at this spot. Units in terms of kilometers, nice. MN, assuming the lines are straight. Okay. So this is just asking you, here's a fixed location, here's two separate points. Find the distances between both with respect to D, and then figure out which is the shortest one. So basically just doing this again, but now instead of adding them up, you're just doing which one's bigger or which one's smaller. Gradients. One thing I didn't quite touch on in that was the relationship between tan theta and gradient. So one of the things you'll look at in circular functions, if you haven't already done circular functions or trig ratios, same thing, is that tan theta can be used to calculate the gradient. There's a bit of a proof behind that. I'll sort of just let you take that for granted right now if you're not already aware of it. Maybe even double check the either the theory in the circular functions chapter on this, or if you have access to my notes on them, you can also grab a copy from that as well, where I explain it. The takeaway is that the gradient, if you know the angle, can actually be calculated by the tan of that angle. Now, that angle has to be with respect to the horizontal in the anti-clockwise direction. So horizontals here, depending on where you choose to take your angle, you're just going to essentially like vertically shift where you consider the horizontal component to be. So in this case, this is your horizontal. You could also take it from here. It's the exact same angle. And the angle is in the anti-clockwise direction from there. So if we think about a circle that was situated on the axes, then we're going in the anti-clockwise direction. So yes, if you have the angle, you can just plug it directly into tan theta and you get your gradient. What we also know from trig ratios is that the inverse trig ratios also exist. So in other words, if you were to calculate the gradient and then had to get the angle from that, then what you would be doing is the tan inverse of that thing, They didn't seem to show it here for whatever reason. I'll just do it on the CAS real quick. So through the gradient method, we would do the rise of a run. So a rise of from 2 to 7, a run from 3 to 5. You do that calculation, you get your gradient. If we go ahead and do tan inverse, which is located on this CAS in the trig button here, you put in that number that we just calculated, or the book did for us, and well, mine's in radians, so let me just convert that to degrees real quick. What's that? So I want to put, yeah, divide by pi, and then times 180. That gets us to the 68-ish degrees for that one. Point of order, probably best to leave your CAS in radians mode. Actually, it's not even an issue for you guys because you can just click this button up here. If you have this CAS, even the other CAS, you can click the button that says rad or deg for degrees or radians. Mine is an older model that does not do that, and yes, I will say that every lesson that this comes up because I hate it, but it's fine. If you want to do the manual way of changing document settings for whatever reason, it's in here, at least for this CAS. So you hit 5 for settings, 2 for document settings. There's a whole bunch of things you'd probably want to practice or play with here. Angle was one of them. If you'd end up doing spec, real or complex is going to matter. Calculation mode, please have it in exact. If you have it in auto, sometimes it will give you a decimal and you won't be too sure whether or not there is actually an exact form of it or not. So if you give it an exact, you're forcing that to happen. And you can always get to the decimal by just control entering. That'll be the main thing. This thing over here is just another spec thing. Yeah, have a play. If there's anything you want else to play with there. Yeah, that's the only other thing to touch on there. Making sure doing the inverse tan or basic just tan theta, the relationship between the gradient and the angle. I think we're probably all fine with calculating basic gradients. Maybe we'll just touch on that angle stuff, which actually is going to be tough if you don't have your CAS. Never mind. Maybe we'll leave that then. Let's go with the harder version of the gradient stuff. See if we can handle that. So it's gradient between 2 points, but the points are in terms of letters instead of numbers. Question 5a.
-2.
Yeah, real quick, -2. That's it. In this case, all the a's cancelled out pretty easily. Nice. That's just a copy. In this case, you have point, another point with a letter, but you also have gradient. In that case, you would just know ahead of time that your gradient equals 6. Do the exact same equation. The equation has one unknown in it. These are technically doable tech-free. It just depends on how well you know the trig ratio, or the what are they called again? The angles for the unit circle that belong on there. Yeah, let's do a sneak peek actually, if you haven't already seen it. Now let's see, what's that? Definitely not in linear. Circular functions, unit circle. This is the thing I was referring to earlier with the circular functions and the related angles in there. What you'll notice is well, apparently an add as well. 30, 45, 60, you'll start seeing some of those. Like there's your 45, there's your 60, 135 over here-ish. Each of these correspond to a particular value, and early on, what you'll find is all those are just going to be either 1 or -1 for a gradient. I won't go into too much detail as to why, but just kind of imagine, if you imagine like literally holding up like a ruler off your table at a 45-degree angle, that is taken as gradient of 1. It's got an equal rise and an equal run, so it has a gradient of 1. this is just going to be -1. It's just on the other side of the unit circle there. So if you think about this being located there, drawing a straight line between those 2 points, it's effectively just a 45 on the other side. And since it's going down, you consider that a negative gradient, -1. And these ones you're just not going to be able to do without knowing much more on the unit circle. This is like a lot later. I don't think you would have... Have you had a look at this Vivan before? Maybe you might have seen something like this.
Yeah, I've seen it before. I haven't like learned it.
Yeah, I don't... Because I know maybe some year 10s have a look at it. Or at least you have a look at trig stuff a little bit. Maybe not these though. But yeah. That's that. Let's see what else we can have a look at. Equation of straight line. Just find gradient and y-intercept. Cool. That's kind of whatever. Date gradient and y-intercept. Yeah, like that's the gradient spot, that's the y-intercept spot. Pretty simple stuff. We didn't quite look at it, but finding the equation between the equation of a line that connects 2 points, a little bit different to the distance equation. We actually want to find an equation that describes the x and y values rather than the distance between them. There's a couple of ways you can do the equation between 2 lines, 2 points rather. One of them is to do just a basic y cos mx plus c simultaneous. So basically you set up your own version of this with y equals mx plus c, y equals mx plus c, and you shove in an xy pair into each of those. And you would solve for m and c in that circumstance. The other way would be to, what's it called? The gradient point formula, which I will pull up. I think that's all about in calculus, actually. I don't think I wrote this anywhere in linear. Implications, tangents. It's this thing here. So you keep the y and the x as the thing for the equation, and you sub in the y1, x1. And if you don't already have the m, which in this case we didn't, we had 2 points, you just rewrite that m as that. So the rise over run equation. So what you essentially end up having is, God damn it, I didn't write it anywhere. Take that, shove that there. And then you've got your, all you do is rearrange for y, and then you've got your y cos mx plus c. What else needs to be shown? Graphing straight lines. No, graphing's whatever. Although magnitude of the angle will be, maybe I'll just do a live demo of one of these. What's a good one? Probably this one here. So we got 3x plus 2. As soon as it talks about angle, we know the relationship between angle and gradient. So we should immediately be thinking that tan theta is going to be relevant here because it's the trig ratio that bridges gradient and angle together. Whenever you're doing any kind of question, when you're trying to solve for a variable, one of the first things you're looking for is what equations have those variables in them. So in this case, we have a gradient of 3. So if we know the gradient is going to be 3, what should I do on my CAS to figure out what the angle that would therefore have been for this?
And the inverse of 3.
Tan inverse of 3, absolutely.
Whilst you're in degrees mode, I think.
Yeah, it doesn't tell us degrees in this one, but yeah, like you would very typically use degrees. It'd be very weird to do it in terms of radians. But yeah, you take that. If you leave it in radians, you'll get that, or if even worse, if you control enter, you'll get this, which doesn't make or seem to make any sense for degrees. But yeah, converting to degrees, just a matter of divide by pi times 180, or just click the button on your CAS. So that should come up to a 71 degree angle, which should kind of make sense. A gradient of 3 as compared to a gradient of 1 is steeper, So if we know a gradient of 1, let's say it's that's 45. Gradient of 3, 3 times that, it makes sense for the angle to be bigger on that one. That's another way you can sort of double check and make sure, hang on a minute, did what I did actually make any sense or not? We always want to be doing that when we're actually in an exam or SAC scenario, doing very quick mental checks to say, hey, did what I write actually make any sense at all? Cool. There's a whole bunch of stuff. So the agenda for these lessons is not necessarily to go through every single question that's on that list. It's more so to introduce the topics and clarify any key concerns with them. So don't feel like we have to have gone through everything, nor should you necessarily have to do everything in your studies either. You know, you can use a bit of discretion. If this stuff is super easy for you, just do a few other questions and then move on to the next thing, right? Keep it fresh, but don't like spend all of your time on it. There's going to be better things to do, focusing on specifically the things that are actually slightly difficult. That's about it for today. If there's any further questions, I'll be happy to stick around for a little bit. Otherwise, I'll leave you guys to it.
Thanks, Chris.
No worries. Take care.
Oh, thank you. I have a question about after this class, right?
Mhm.
Do I do what are the modules? I saw something in the classroom tab.
Yeah, the modules. So those are, I think I mentioned it earlier, one of the things I've created as a supplementary resource to the class stuff is the course that's in there. Right, so you'll notice that all the modules are functions, relations, calculus, basically all the stuff in there. All of these things that I was teaching out of, those notes that we're talking about, are located in those. And that's just a one-time purchase of $70 for the whole thing, all the way up until year 12. You get all of that as well as a bunch of practice SACs as well. So if you want to get access to these things because you like the way they're written for whatever reason, that's how you grab those. They're not a necessity, of course. You can see even the textbook does teach things a little bit in there, and you also have these recordings as well if you want to look at those. So not a necessity, but probably a nice to have, and it's when you
So I can
consider.
get all these notes and the past recordings for 70.
So class recordings are free, actually. Those are in the past recordings tab. That should
Okay.
already be unlocked for you. So that's why I'm saying you can just use those if you're on a really tight budget. But, you know, it's $70 and it'll take you through the rest of VCE methods. It should be an easy enough thing to get a hold on if you want it.
All right.
But yeah, that and the practice SACs in there as well.
Yeah. Thank
Easy.
you.
No worries. I'll leave you to it. Are you going to come to the next two, or
I'll see if I can. I probably will, but next year is Tuesday and
Tuesday, Friday? Yeah.
Tuesday and Friday. Okay.
Yeah, so let me know, I guess, if you're going to attend or not. That way, because as I said, I will tweak things a little bit for if there's low attendance, we'll make it more applicable to what you're currently doing.
Are the next two classes the same topics or is it different?
I didn't actually check the topic. So the catch-up class on Friday is always going to be a repeat of the class 1 and class 2, so the Monday and the Tuesday. So that'll always be a repeat. Unless, of course, there's only like a couple of people attending and we can just do whatever makes sense for you guys at that time. So yeah, make use of the Google form on. Did you see the Google form link for the calendar tab?
Yeah, I think I did.
Yeah. So if you have a specific thing you're looking to go through, like Upraj has already done a full year with me. He's done all this stuff before. So if you want to do something specific, like let me know and we'll be happy to circumvent the curriculum for it.
Okay, yeah.
Cool. All right. If you have any further questions, there's WhatsApp, there's the school thing, and I'll leave you to it.
Thank you.
Take care.